I'm Professor Rad, and this is Precalc video 1-8, Continuous and Smooth Functions. Think back to when you were a kid and you were first learning adding and subtracting and even the concept of numbers. When you first learned how to subtract, you probably learned that you could do something like 5 take away 3, but you couldn't do 3 take away 5, right? And this is because at that time, numbers were very concrete objects. So if I only had 3 apples, you can't take 5 away from me. But if I have 5 apples, you can totally take 3 away, right? And then I would be stuck with 2 apples left. So in this video, we're going to talk about the definitions for continuous and smooth in the same way. Right now, we are at a place where our understanding of math and our tools in our toolkit allow us to think of subtraction in terms of 5 minus 3, but we're not at a place where we can delve deeper and think of subtraction in terms of 3 minus 5. Of course, I'm using this as an analogy, right? I'm saying we're at a place where we can understand the concepts of continuous and smooth in a particular light, but these are not the precise or formal definitions for these concepts because we don't have all of the tools in our toolkit yet to be able to do that. So once you get to calculus, you will see a much more formal and precise definition of continuous functions and also for smooth functions that incorporates functions that we're kind of discarding at this point, much in the same way that when you learned about subtraction, you only thought about 5 minus 3 and you didn't think about 3 minus 5 until you were a little bit older and could think of things like debt or numbers having both an amount and a direction. So you could conceptualize what -2 might mean. So right now, our definition for continuous functions is going to be a function that could be drawn without lifting up your marker or pencil or pen. So if at any point you needed to stop, pick up your marker or pencil or pen and put it someplace else to continue drawing the function, then we'll say that is discontinuous at that point. If you can draw it without ever needing to do that, then it's a continuous function. For a smooth function, a function is going to be smooth if it has no sharp corners or cusps. So we're going to look at a few examples of these, but I wanted to stay out of the way of the definitions in case you wanted to pause and copy those down. And I think what we'll do to think about these concepts is we'll talk about our common functions that we did back in an earlier video. So let's start out with the identity function. So the identity function, if I wanted to sketch this real quick, right, is a line going through the origin with a slope of 1. The identity function is both continuous and smooth. It's continuous because in order to draw this, you never need to pick up your marker or pencil. Now, we're also talking theoretically here if you have infinite drawing capabilities, right? Obviously, I can't physically draw this forever because I would perish in that attempt, but we can indicate that it goes on forever without a break. It's smooth because it doesn't ever like, right? It never takes a sharp corner or turn anywhere. So the identity function is continuous and smooth. Let's think about another one. Let's talk about the reciprocal function. So the reciprocal function had asymptotes, and it essentially looked like this. So the reciprocal function is not continuous, but it is smooth. So the reciprocal function is not continuous, but it is smooth. The reason it's not continuous is because I draw this bottom left-hand piece here, and there's no way for me to go from this bottom left-hand piece over to this top right-hand piece without picking up my marker. So the reciprocal function, we would say, has a discontinuity when x is 0, because that's where the break happens that I had to pick up my pen or my pencil or marker. So we would say it is discontinuous at x equals 0, because that's where the break occurred. Now, the reason that we're saying that it's smooth, it does have some turning to it, but it's a nice smooth turn. It's like a gradual descent and turnaround. It is not that, right? It's not a sharp angle. So a sharp angle is not smooth, but this gradual turnaround is smooth. So let's look at something else. Where did my eraser go? There it is. Let's look at the absolute value function. Do you remember what the absolute value function looked like? So that's the one that's only in the positive y space, and it looks like a v. So our absolute value function is a continuous function because I can draw it without ever having to pick up my marker. So it's continuous, there's no asymptote, there's no hole. However, it is not smooth. Now, the reason the absolute value function is not a smooth function is because when it turns around, it's a sharp point, it's a corner. So it doesn't slowly approach that turnaround and kind of gradually, turn through that point. It just goes boom, boom, right? So it's a sharp corner. It's like a cusp. So that means it's not smooth. So these are some of our common functions that we talked about earlier. What I'd like you to think about is, I think there were 11. So that means there are 8 other functions we haven't talked about yet. So think about those 8 other functions and whether they would be continuous or smooth. They could be one and not the other, such as the reciprocal or the absolute value function, or they could be both, like the identity, or what would it look like if they were neither? So think on that, and we'll probably talk about that in class. It'll probably be on one of our check-ins, but this is just a real quick introduction to the concepts of continuity and smooth. Hope that gives you some idea of what these properties are going to look like. In our next video, we'll talk about some more properties of increasing and decreasing. So I look forward to seeing you then. And in the meantime, have a wonderful day. Bye.